Let's get some more practice with this, fairly straightforward method. See what can cause it to be less straightforward and get some more interesting examples as well. No more comfy cozy anymore. The beanie's coming off, getting warmed up, lots of energy, more complicated problems. Let's get to it. So let's just continue the last example, find the area between these two curves. And part B is going to say between the curves, f of x equals 5 minus x squared, and g of x equals 1 minus x. And that's it. This doesn't tell you the region. It just wants the region that's trapped between these two curves. So we have to find graphically or analytically what is the x coordinates, where are the points that these things get trapped between. All right, so there's a couple of ways of graphing this. Does this quadratic factor? Nope, I don't think so. So in general, we do know that this is an open quadratic. We could find the vertex. Let's just graph this on Desmos though. We could do it, just save some time and get a picture. So f of x is equal to 5 minus x squared, downward facing parabola, as expected. And g of x is going to be 1 minus x. So we can graph this, we can see this. And before I click on this, don't look too much. Don't look. Don't look too much. Just the shape, All right, we can find these intersection points analytically if we wanted to. It's fine if you looked. All right, but what's going on is we have, this red curve and this blue curve, and we're looking for where do they intersect. Because if we can find these intersection points, that's our region of integration. Also, does it matter that blue is negative, that we're negative here? Remember, integrals are net signed areas. Well, I'm not going to answer that question. Let's just pretend like it doesn't matter. And let's see if we're right. Let's see if our answer kind of makes sense. Okay? So, let's set this up and see what happens. So before we set it up again, we don't know the regions of integration. We have to find their intersection. Okay, so they intersect when they're equal to each other. So that's going to be when 1 minus x equals 5 minus x squared. There's a couple of ways of solving this system of equation. We have two equations. We're looking for two values. A couple ways of solving it. One is substitution. That's what I did. Y is one thing, Y is another thing. Let's set those things equal to each other. Sometimes you'll use another method like substitution, or maybe you'll solve for x. This method really works out here because we add x to both sides, and look what happens. They cancel out. And if we subtract 1 from both sides, then we get 0 is equal to 4 minus x squared. We can either factor this or use the square root property. Remember, factoring only works for polynomials if it's set equal to 0. Most of you probably will prefer the square root method, so I'm going to show you this method. If we factor it, set equal to 0 and factor it, we're going to get that x is equal to plus or minus 2. And that gives us our region of integration. We could find the y coordinate as well by putting this back into either one, because the y coordinate is going to be the same. That's what we found out. But we don't have to. We don't need the y coordinate here. So now our integral is going to be the integral from -2 to +2 of the upper function, which is the parabola, minus the lower function. Again, I'm going to distribute that negative. We're subtracting this function. It becomes -1 plus x. With respect to dx, do not forget this. This is really important. And it doesn't feel important right now, but especially in Calc 4, it becomes more important. And also, a little spoiler, in example C, it becomes important. In example C, this dx becomes very important, and I'll show you why. Also, in use substitutions, the variable here was very important. dx was very different from du. So now let's simplify and evaluate. This is a good opportunity to practice your arithmetic. Pause the video, try to finish this integral, and see if we get the same thing. All right, so you could collect like terms, use the power rule, blah, blah, blah. I'm just going to save us some time, and I'm going to use Desmos. So we're looking at the integral from -2 to 2 of f of x, which we wrote down, minus g of x, which we wrote down, dx. Now we're going to get 10 2/3. So 10.6 repeating is 10 2/3 is a mixed number, which is 32/3 is the exact answer here. So, did we make a mistake, or is this area stuff okay? Well, if we wanted to, we could split this up into a couple different regions, right? This first area, everything's super straightforward on this first area. Just red curve minus blue curve. And now this second area, we can just take the integral, right? So this first area, right, is the integral from -2 to 2 of just f minus g. Well, the second one is the integral from 0 to some number. It doesn't matter what it is, whatever that is, whatever this number is right here. Let's just call it a for now. We don't need to find it. Of this parabola, f of x dx. Now, what is this green area? Well, the green area is the opposite of the integral from 0 to a of g of x. So before we even finish by getting this last piece, look at blue plus green. And it's opposite, remember, because the integral gives net signed area. We're looking at total area. So the integral is going to give us a negative number. We want to turn that positive, so we add a negative sign here. Well, look at combining the blue and the green. If we combine the blue and the green, what do we get? We get the integral of f minus g. So even though g is going negative, it actually doesn't matter here. If you split it up into these pieces, you can still see that adding the individual areas together is still resulting in f minus g. So it doesn't matter whether a function's positive or negative. It only matters which one's on top. And again, there's one more area we could fill out right here, and you could do another one, but you'll get the same result. This does kind of make sense here. Good. Now let's do a more interesting problem, shall we? Find the area between f, the same f, but a slightly different g. T is less than or equal to 5. So now instead of knowing what g is exactly, I'm saying g is some line. G is some line with a -1 slope. But I'm saying do this for any y-intercept less than or equal to 5. So let's visualize this. I'm talking about the same f, but g now is t. So when t equals 1, we have 1 minus x just like before. And, oh, you can switch this to fractions. But as t changes, the y-intercept, t is the y-intercept. Look what happens with the y-intercept. It's changing. So the smaller t is, the bigger this area should be, right? And the bigger t is, the smaller the area between the curves get. And when t is 5, there's no area. When t is bigger than 5, well, now there's not an enclosed region anymore. That's why we have t be less than or equal to 5. So we're going to solve and find this area for any value of t. So unfortunately, notice that where they intersect is different depending on what t is. So we're going to have to find that intersection. So when are they equal? Well, we'll do the same thing. Now we have two equations. It looks like we have three variables, but remember, t is a constant. We just don't know what it is, but it's just some number that's less than or equal to 5. We're solving for x or y. We're solving for both. So let's do it just like before. So again, this is still y equals. This is still y equals. Set the y's equal to each other. If y is one thing and y is the other thing, and we want them to be equal, then their things have to be equal as well. So we're going to get this just like before. And just like before, we're going to add x to both sides, which very nicely cancels it out. Thank you, Jason, for coming up with a nice problem. You're welcome, student. And then let's subtract t from both sides. When we do that, we're going to have 5 minus t minus x squared equals 0. Now, this doesn't look as nice. But remember, t is just a number. So this is just some number minus x squared. This is our variable. So we have a squared variable. We have no linear term in x. There's no x lying around, only an x squared. And that's just some number. Again, factor or use the square root property. And the last one we factored because it was a difference of squares. 4 was a perfect square. X was a perfect square. Here, maybe this will be a perfect square, maybe not. We don't know what t is. So let's use the square root property this time and add x to both sides. Add x squared to both sides. Well, now we can take the square root of both sides and get x. X will be plus or minus the square root of 5 minus t. And this is true. This is their point of intersect for any t. So this is not our final answer, but it is important. In part B, t was 1. And we got that x was plus or minus 2. Well, let's visualize this with Desmos. I'm saying that these intersect when x is plus or minus, so let's start with the minus, the square root of 5 minus t. And let's plot this as a point. What's the y value? The y value is the function evaluated at this location. Look at that point. And then we have another point. That was the minus version. We have another point at the plus version. There it is. And as t changes, notice that these points, these plus or minus the square root of 5 minus t is the x-coordinate. The y-coordinate is what happens when you plug that into our function. This always will give us the intersection of these two functions. So no matter what t is, we have found the region of integration. Pretty fancy, right? And this is a lot of times a struggle for a lot of students, and that's okay. But I want to convince you that this is awesome. Okay, it doesn't just look pretty, although I think it does look pretty. This is like one of the foundations of mathematics is coming up with formulas, doing more work so that you can be lazy later. So if we can generalize things like this, then it's true for any line that follows this pattern. And of course, this is maybe a sillier example to show that this formula is nice, but in general, like that's where formulas come from. Is someone saying, well, you know, I could calculate the area of this rectangular field every time I have a different rectangular field, or I could calculate the area of a rectangular field for just any width and any length. And they do the calculations. They say, well, the area is an L times a W. And that's true for any L and W. That's what we're doing here. That's all these parameters and these constants are. They're just giving us an opportunity to come up with formulas. And so that's why doing things with parameters like this, they're harder, but most of the time they're going to be much more useful. And this is just more practice. It's cool. So we have the integral now from the lower bound, which is going to be negative square root of 5 minus t, to the upper bound, positive square root of 5 minus t. I think one of the hardest things about doing things with parameters like this is the visualization. So I'm hoping that this really does help. It helps me, and I'm very happy to be teaching at a time when we can do things like this, If teaching this class 30 years ago, it would have been harder to show this. Also, I would be a baby, so that would be harder too. Anyway, now it's still f minus g, just like before. This time I'm not going to skip it. This time let's do the nitty-gritty together. Minus g, so that's going to be minus t plus an x when we distribute. And now let's calculate this definite integral together. Or again, it's great practice if you want to pause the video and try to do it yourself. Remember, t is just a constant. So what's the antiderivative of a constant? Just that constant times x. So if we can, again, just cancel these x's, which is really nice. Thanks again, Jason. You're welcome. Take the antiderivative. We're going to get 5x minus x cubed over 3 minus t times x, all evaluated from negative square root of 5 minus t to positive square root of 5 minus t. Remember I said that the dx matters? This is why. If this were a dt instead, it'd be a totally different integral. This tells you that x is our variable. X is what we're taking the antiderivative of. Just like the difference between ddx and ddt are different if there's multiple variables. So the dx is very important. It tells us we can treat t as a constant. Now we just plug this in. I don't know how this is going to simplify, how far this is going to simplify, but we'll do a little bit. So what we have is plug in square root of 5 minus t minus, let's write this as 5 minus t to the 3 halves. Or you can write it as the square root cubed. They're equivalent. Minus t times the square root of 5 minus t. And we're subtracting basically the same thing, but with a negative. Oh, interestingly enough, this is a perfect opportunity. Let's save ourselves some work using what we know about math. Look at our integrand. Look at this function. This is a number minus x squared. Look at this integrand. It's some number minus x squared. We're really getting full. Let's have another one. Look at this integral and tell me what you see. 5. Wait, what is it? 5 minus t minus x squared. No matter what t is, what do you notice about this integral that we've talked about in this class? This is an even function. What do we know about the area under the curve of an even function from negative a to a? If we're looking at this area and our x coordinate on the left and our x coordinate on the right are just opposites, well, it's just double one of the areas. So instead of plugging in the negative and having a whole nother term here, we can use what we know about even and odd functions to just slap a 2 out in front and save ourselves some work. So that's properties of even functions for integrals. And you could simplify this a little bit more. Let's combine these two terms and distribute the 2. That's going to give us 10 square root of 5 minus t. And then that's this whole term. So we can write it like this. So I'm combining this with this. Factoring out. Oh, no, we can't do that. Yeah, we can't factor out a 10 from both. We can factor out a 2 from both. And then it's going to be 5 minus t in here. So now, that's what happens when we combine these two terms. There's a lot of ways you can simplify this. I think, My music just started playing. Luckily it's muted, you can't hear it. And I actually think there's a better way of simplifying it. Let's factor a square root of 5 minus t out of everything. So we also want to factor out a square root of 5 minus t on this guy. And that's going to leave us with 1/3 5 minus t squared. So I wrote this in the wrong order, but it's just this guy is this guy. Factoring out square root of 5 minus t, we're left with a 5. This is this. Factoring out a square root of 5 minus t, we're left with a negative 1/3 5 minus t squared. Oh, no, we're not. It's not a squared. This is what happens when you try to do too many things at once. We had 3 halves. We took out 1/2. Now we have 2 halves left. And then this last guy is this when you factor out a square root of 5 minus t. This is why you don't skip steps, my friends. I skipped steps to show you the reason why it's bad. Let's go with that. All right, and then we can simplify a little bit more. It's also a little better if we factor out a 1/3 out of everything. So let's factor out a 1/3 out of everything. I won't skip steps this time. Factor out a 1/3, we get 15 minus 3t. Now it just becomes minus 5 plus t. And we can simplify our final answer to be 2/3 square root of 5 minus t times now just 10 minus 2t. Oh, I said this would be our final answer. Because 15 minus 5 is 10. Minus 3t plus t is minus 2t. But we can actually factor out another 2. We get 4/3. Again, a lot of times in math, the hard stuff. Oh, okay, we're still not done. What else can we do? What's the square root of 5 minus t times 5 minus t? 5 minus t. Was there an easier? I feel like this simplification is crazy. I feel like there was probably an easier way to do this integral that wouldn't have resulted in so many steps. Hopefully this is the area. We can check our answer with Desmos, but let's also check our answer another way. We know the result when t is 1. When t is 1, this area should be 32/3. What happens when t is 1 here? We get 4/3 times 4 to the 3 halves, which is 8. 8 times 4. Oh, thank goodness. 32/3. Thank goodness. This doesn't prove that we're right, but it's almost a proof that we're right. It's all right, not almost a proof, but it's very reassuring. So we found that this area for any value of t is going to be this guy. Good practice right here. Good practice. All right, let's see this. Let's see this with Desmos. We got a lot going on here. Instead of looking at the integral from -2 to 2, let's look at the integral from negative square root of 5 minus t up to positive square root 5 minus t. And let's compare that with what we think the integral should be. 4/3 5 minus t to the 3 halves. Watch these numbers as t changes. Can I move these around? Great, I can. So compare these two boxes as t changes. Oh, and we'll leave them in the same form. Look at that. Look at that. And as t gets close to 5, the area gets really small. When t is 5, the area is exactly 0. And as t gets less, the area grows bigger and bigger and bigger. We calculated it for any value of t. Look at that. That's cool, no? And it's really good practice as well. I don't think you have any of these in the homework assignment. And I didn't want to tell you that at the start. But this is just extra fun. I'm trying to trick you guys into having fun. All right. Trick you into math fun. Let me know if you have questions. This is cool stuff. And it'll pop up in math and science. Basically any science stuff. This kind of idea is everywhere. But yeah, there you go. Enjoy. Bye-bye.